Hello, everybody, and welcome to Unit 7, Part 2 notes. And today we're going to be talking about molecular geometry. All right, one of the reasons why we do Lewis dot structures is to try and figure out the geometry or the shape of molecules. All right, shape of molecules is very important in determining the properties of these molecules, and that is going to be our focus. When we're talking about shape, we use something that is called VSEPR theory, which we call VSEPR theory. I know it looks more like VSEPR, but it's called VSEPR theory. And what that stands for is valence shell electron pair repulsion. All right. So what you should take from that is this idea that electron pairs or bonds, right? Okay, want to get as far away from each other as possible. And this leads us to different shapes. All right, and we're going to go through those different shapes. All right, to figure out our shape, the first thing you're going to do is a Lewis dot structure. Great, we've covered that. You are then going to look at the central atom, and count how many shared versus unshared pairs are around there. All right. If you see a multiple bond, you're just going to count that as one shared pair. So even if it's a double or a triple bond, we're going to count that for the purposes of shape as one shared pair. When we're discussing this, we're going to talk a little bit about angle. And when we talk about bond angle, it's the angle between the bonds. And I'll show you that as we go through some examples. All right, so you have a chart to fill out. Okay, that should look very similar to this. Okay, so let us start out with our first example. And our first example is CH4. All right, so CH4, better known as methane. All right, so I'd like you to pause the video and go on ahead and do the Lewis dot structure for this. Okay, so you should have found carbon has 4, and then we have 4. Great, so we're dealing with a total of 8. Our Lewis dot structures, and I'm going through these pretty quickly because we've done this before. All right, so there's our Lewis dot structure. Okay, all right, so now to determine the shape, I am going to look at the central atom. How many shared pairs around the central atom? Well, it's 1, 2, 3, 4. There are 4 shared pairs. Around the central atom, there aren't any unshared pairs at all. All right, so 0. Okay, when you get into a situation like this, according to our VSEPR theory, all right, remember those bonds want to get as far away from each other as possible. Remember, molecules are three-dimensional though. All right, so I do have a model here. And in our model, we have our carbon is represented by the black and our hydrogen's the yellow. All right, and then the bonds are these sticks. Well, these bonds want to get as far away from each other as they possibly can, all right, without getting closer to the other one, leading to this shape. This shape is called a tetrahedral shape. All right, so let's get that down. That is a tetrahedral shape. All right, and the angle between these bonds, all right, is 109.5 degrees. And again, when I'm talking about bond angle, I'm talking about the angle between the bonds, okay? Now, if you go on in chem, you will kind of learn to draw these molecules the way to sort of at least represent the shape a little bit on a flat surface. And here's how you would do that for methane here. Again, we're not going to be asking you to do this, but just so you know. So if I were to put this on my hand, this is a flat plane, right? I see that 2 of the carbons are on the same plane as my hand. So I just draw sticks for those. All right. Then one's going backwards and one's coming out towards the camera. So to show that, all right, I'm going to just do little dotted lines backwards and then kind of show little wedges going forward. That's just to give a little bit better idea of the three-dimensional characteristics of a tetrahedral. Again, you're not responsible for doing this, just wanted to show you. All right, so now let's go on to our next example. And our next example is ammonia, NH3. Again, feel free to pause the video if you need to. All right, so we're gonna go 5 from nitrogen, 3 from hydrogen, dealing with 8. All right, great. So I have my nitrogen here. And then the 2 dots there on top. All right, so we're going to go ahead and count up shared pairs, 3. Unshared pairs, I have 1. All right, so what happens here is I'm going to go back to my tetrahedral shape because this is kind of my basic shape. And instead of having 4 bonds coming off of the center, all right, I only have 3. And then I have this unshared pair. Unshared pairs take up a lot of space. All right, so let's talk about unshared pairs. You might want to jot this down. All right, so take up more space. You can think of these, you can think of a pair of electrons kind of like a balloon. And if you and I were both pulling on 2 ends of a balloon, it would be a skinny balloon, right? But as soon as you let go and I'm just holding on to that balloon, it's going to be a nice round fat balloon. Same thing happens with these electrons. So what ends up happening is I have, compared to the tetrahedral, I have lost one of the bonds. I now kind of have a big balloon on top of here. And what's going to happen is it's going to actually make the angle between these 3 get closer together, giving us a different shape. And this shape is trigonal or trigonal, however you'd like to pronounce it, pyramidal. All right. And the bond angle for a trigonal pyramidal is 107 degrees. That's not one that I'd expect you to be able to geometrically figure out. All right. But notice as I have more unshared pairs, my bond angle is getting smaller, all right? To draw a pyramid, okay, what we typically do is we think of a pyramid, right? So we draw it, and again, it's 3-dimensional, so, you know, little wedges, however you want to do it, or people do just draw it like this as a shorthand, but you always have to include that unshared pair, all right? And remember, this bond angle is getting smaller because that unshared pair takes up more space, okay? If you notice, my little unshared pairs look like a little bit of an alien or a chicken's head, but there you go. All right, so let's go on to our next example. Our next example is an important one, a really important one, and that is water. All right, so for water, we're getting 2 from the hydrogen, we're getting 6 from the oxygen, gives us our magic number 8. Okay, fantastic. Oxygen is my central. All right, we may first draw our waters like this, but we're going to find out soon that that's not a good way to draw our waters. All right, so let's look. Shared pairs 2, unshared pairs 2. All right, so what's going on in this situation? Okay, now I have a situation where I have my 2 pairs, or my 2 bonds still, but now I'm going to have 2 big balloons. So this bond is going to get even smaller. All right, and it actually gives us a bond angle of 104.5 degrees, and it gives us the very exciting name of bent. All right, so that is a bent molecule, okay? How we should always draw water, and this is really important, I'm even gonna draw it over here so you remember, all right, is to show this bent structure, I should have given myself more room, is we always draw it, and you should remember this from biology, as a bent molecule. I'm gonna draw that bigger over here. All right, so we've got our oxygen, hydrogen, hydrogen, to remind us that this is not a linear molecule, this is a bent molecule, and that is for water. All right, next example is BF3, and I am going to tell you that boron is an exception to the octet rule. All right, boron only wants 6 electrons. It is an exception. All right. So when we go on ahead and we deal with this one, we're going to say, okay, well, boron, how many valence electrons? It has 3. Fluorine has 7 each. All right, so that's 21. So we're dealing with a total of 24. Okay, so I'm going to draw boron here. Is my central, then F. And remember, I'm telling you, boron is an exception. It only wants 6. So it's happy just the way that it is. Okay, great. So there's my Lewis dot structure for BF3, boron trifluoride. All right. Now, how many Now remember, because this is the first time this has come up, when we're counting shared and unshared pairs, it is just around the central atom. You see all these unshared pairs around fluorine. We don't care about that. We care about that central atom. So how many shared pairs? We have 3. How many unshared pairs around boron, around the central? We have 0. So now, when I'm looking at this, I can say, okay, well, I have 3 bonds around a central point, and they want to get as far away from each other as they possibly can. That actually gives us this shape. All right, and this is actually one, and this is a flat planar shape, okay, and we call this trigonal planar. And this is certainly an angle that we could figure out, right? You take a circle and you divide it in 3. Trigonal planar's angle is 120 degrees. And how we would draw this one, okay, would be for this. And just to show what's going on with that, okay? Typically, when we're just drawing these quickly like that, we're not including the extra electrons around the outer elements, but when you ask for Lewis dot structure, you have to. All right, our last one is our carbon dioxide. Okay, and we did this example the other day. If you recall, carbon dioxide has a Lewis dot structure where you have double bonds on each side of the carbon. Okay. All right, so again, around the carbon, how many shared pairs? There are 2. We count double bonds just as one shared pair for the purposes of shape. So there's 2 shared pairs, there's 0 unshared. Again, all we care about is the carbon. All right, so that's going to cause this situation, 2 bonds getting as far away from each other as possible, and that's going to be a straight line. That is linear with 180, or I should do this for you, 180 degree bond angle. So we call this linear, and that is a bond angle of 180 degrees. And we would just draw this. Linear is a straight line, so nothing too exciting there. Okay, great. So we're going to do a lot more practice with this. There are more than just these 5 shapes out there, but these are just the ones we're going to focus on in this unit. All right, have a great day, everybody.